Welcome to the Contagious Code podcast, where we dive deep into code, learn practical skills, celebrate the beauty of engineering, and eliminate imposter syndrome. I'm Tejas Kumar, and I've been building on the web for over 20 years at places like Vercel, Spotify, Zeta, and more. Today on the podcast, my guest is Dan Bochman. Dan is the co-founder of Fashion AI. We also had an episode with his co-founder Aya on the podcast in a previous episode. Dan is also an expert and an academic on AI, specifically in the focus of vision models and computer vision and image generation. And today's episode is a deep dive on that. And when I say deep dive, I mean deep dive. We talk about from the beginnings to today, what it takes to generate images with AI. We also explore diffusion models and how the process of diffusion even works through a really, honestly, deep dive into the subject. After this episode, you'll be able to understand image generation with AI. You'll be able to understand models like stable diffusion, and you'll be able to even understand what diffusion even means in how models like OpenAI, for example, with the Sora model, how they can generate video, or how fashion generates images, and so much more. This really is a special conversation and is a wealth of information. If you're interested in any of these topics, this is definitely the episode for you. I'd like to offer this to all of you at no cost, and the way we can do this is through partners, because this is separate to my day job. And so let's take a moment to acknowledge them, and then we'll get into the episode. The Contagious Code podcast is partnered with Code Crafters. Code Crafters is a great way to level up your coding experience and skills by having you pick a programming language like Docker, Python. Docker isn't a programming language. Like Python, JavaScript, TypeScript, as well as pick a tool like Docker, Git, and Redis. And what they have you do then is build the tool in the programming language. So like, hey, let's just rebuild a Docker in TypeScript, and they guide you, they hold your hand along this process. And by doing this, you get better at actually the tool because you understand how it works, and you get better at the programming languages. You get a 2-for-1 deal. They have a really great free tier, but if you want to start paying, you can get a massive discount if you use the link in the show notes. That's tej.as/codecrafters. The podcast is also, friends with Fashion AI. And so we'll put a link to the episode with Aya, Dan's co-founder, also in the show notes. Hey, thanks for sticking around. Here's my discussion with Dan Bochman. Dan Bochman, welcome to the podcast.
Happy to be here.
I'm so excited to talk to you today because the listeners usually enjoy the AI episodes more. We had a great episode with Aya, your co-founder with Fashion, and that was, people really liked that one. And it's really exciting to talk to you today about the AI side of it. Like with Aya, we talked about the web side of it, the Next.js side of it, but it's nice to get some AI background from you.
Awesome. Yeah, happy to share.
Let's maybe start with this question of latent space. I have a very vague idea of it. So what I'll do is I'll tell you my experience with this, which is laughable, and then we can like fill in some gaps. And I think the reason I do this is because I think a lot of the listeners are basically the same as me here, and so they'd love that information. And we could maybe even touch on like diffusion and other topics. So
sure.
I don't know what latent space is. I know it's a newsletter and a podcast, but by Swix. I used to, in the Vercel Slack, Guillermo's status in Slack was exploring the latent space. What is that? And how does it fit into the context of AI?
Sure. Yeah. So we can answer what is latent space in short for now, but I think it's more interesting to go backwards a little bit to understand why is it even necessary.
Yes.
So to give a quick answer right now, latent space is a space of feature that is different from the natural space. So if we're talking, for example, about images, the natural space here is RGB images. So we are doing a video right now. So you see my face, I see your face. It's RGB space. So we have the 3 channels, and we have a number between 0 and 255 for every pixel. So you could try to do image generation directly in this space. But as it turns out, it's a little bit difficult.
Did people try that before the latent space became more of a topic?
Yeah, exactly. Latent space was a big breakthrough to help do image generation, because doing that in pixel space was very difficult. So what we're doing is not very different from other methods that you probably know, like JPEG compression, for example. So we know, for example, that PNG images are kind of like lossless true quality. But you know that you can significantly reduce the size of images by compressing them to, for example, JPEGs or WebP formats. And for example, the idea behind those is that instead of recording every single pixel in the image, you can do some kind of like wavelet composition of them. You can express them as waves and as frequencies. And if you store that information, you will probably be able to restore the image very, very accurately with differences that you won't be able to recognize with the human eye. So the idea is to take it also to machine learning and to diffusion and kind of like work with a space that is more condensed, that is more information rich with less bits of information there. So every kind of like pixel of that space has a lot more juice in it, like a lot more information in it. We can take a look, for example, at your image right now. We have the background. So
Yeah.
I have a lot of like white, beige, off-white color in my background, and you have a lot of green in that background.
Yeah.
But if you look in kind of like percentages terms, it takes like 50% of our image, both of our images. But it's not interesting at all. And so you could, for example, replace that with all of the top side is like a solid color of some kind of hex code, for example. And then you were able to replace 1000 pixels with just like 3 other coordinates that describe this line of color. It's just kind of an example of how you can replace the features to something that in a lot less words, you can say, or features describe a lot more pixels. So the latent space is just the smartest way that we know how to do this today. Yeah.
The smartest way that we know how to, remind me again, to represent higher quality pixels in a lower quality way.
In a more condensed
Gotcha.
way. So for example, the JPEG compression, what we do with images, these are like classical algorithms. They are deterministic algorithms that people actually like handcrafted the equations, like really smart people handcrafted the equations and the algorithm to do this kind of like wavelet decomposition. But when AI came, it changed everything from image classification to object detection. And also this, people said, why do we have to handcraft these algorithms to how to compress images when we can let AI learn that? Let's give AI image input and try to constrain it to compress this image to, let's say, 1000 features, like a 1000 long vector, and then decode it back to the original images. And
sorry to interrupt you, but can we define features here in an image? Is it just like edges and highlights and colors, or?
You can say that, yeah, you can say that, and you can explore the internal images, the internal features of images that are learned. But yeah, it can be colors, it can be edges, it can be wrinkles, circles, shapes. And the more focused you are on a specific domain, the more features that you get, it will be relevant to this domain. So if you do something in medicine, probably you would have features more related to MRI images. But if you're more into people, so something like eyes and eyebrows and nose will probably be a very profound feature in that space.
And the features are detected by these sophisticated machine learning algorithms that are trained in a specific domain.
Exactly, yeah.
Got it. Okay.
So for example, this latent space that the diffusion models are using, they're basically just trained on the whole web. Like the open images web, all the things that you and I are uploading, and you can find kind of like freely in Google search. And these, we call them variational autoencoders. I don't think it's that important, like VAEs. But their task, different from the diffusion, it's trained before using it for diffusion, is just to learn how to compress these images, to encode them and then decode them.
Interesting. Okay, so this is a really great answer. I love this is honestly one of those moments in the podcast where I'm like, it's so nice to have an expert who knows their stuff, break down a concept in plain English. The great scientist Dr. Feynman was like, look, people, the true mark of understanding is that people can explain it in plain language. And I think you did that, right? So
I
let me
hope.
say back to you.
Like,
Yeah.
in
No,
my,
let's test it. Let's
in
test it. Let me
in
say
my
back.
opinion, we even like jumped too advanced too early, but like I can't like
Yeah.
disrupt the flow.
Yeah, no, it's fine. Let's test it. So the latent space is this may be wrong, but it's okay. We're iterating. It's a lower, almost like a lower resolution representation of a high quality image that you can use to derive new images from. Is that close, far?
Oh, you took it another step forward.
Okay.
Okay, this is why I was afraid of talking about latent space at the beginning, because we are mixing diffusion and latent
Oh.
space together, like they're intermixed very strongly, but they're not.
Okay, can I just, so with diffusion, this was my first ever entry into AI. Maybe, and that's not true. Into like image AI was working with Stable Diffusion, the model, and fine tuning it with Dream Booth. And I'm the layperson, my complete noob understanding of diffusion. I have a design background, and so when I hear diffusion, I think of a photo filter. Like you take an image, right, and you make it a bunch of like dots, like it's diffused. As a video editor, editing the podcast, the diffuse effect is where you fade one image into another. This is what I think of when I think of diffusion. Now, how can we? Are there parallels to this term in AI, and what are they? And can we maybe use those to give everyone listening an understanding of this term diffusion?
The terms are very confusing. They come from a very like thermodynamics background of like particle diffusion, not even what you're talking
Wow.
about, in terms of like proving these equations that theoretically guarantee the results that you're expecting in doing this diffusion process. So this is why I'm saying that it's helpful, in my opinion, to go a little bit further back, and we will visit the latent space, but start like much simpler without all these technical terms, because they're not really explaining what's really going on. So in the simplest terms, what's going on is that we want to generate images. Okay? Not just generate images, we want to generate something from nothing.
Wow. Okay.
And like if we say nothing, for example, what's your intuition about like what's nothing in terms of what's a nothing image?
Just like black, a big black square or rectangle.
Probably everybody think that's the physical intuition. So, but in the information world, black is actually not nothing. It has a lot of information. That it's a black image. So if you're trying to think about like something on your screen that doesn't mean anything and it's turned on, it's not like it's turned off, then noise, just white noise, is nothing.
Interesting.
Black is something. So if, for example, you want to generate images and you want to start from the space that is the farthest away from all possible images, then black is not it. Because if you start from black, then it's easier to generate darker images. It's easier to generate something in the night. And the same for white images. If you are starting from white, then it's going to be easier to generate a white shirt. But noise, just completely random noise, it's the farthest away possible from everything. It's the true nothing to start from. So we already see that we have a different intuition about what's the point of this noise? Why are everybody talking about noise and denoising? It's just that even before diffusion came along, scientists and researchers, they wanted to generate images from nothing. And by the way, it's not only images. Music, like Music Gen and other like audio generating tool, they also need to start from nothing. And nothing is not silence. Especially
It's
in music.
noise.
Just noise is a lot more nothing than silence, because even when I speak, there are moments of silence that are important. They convey information. But if I would be talking incoherently and there would be like, sorry for if it's noisy to the listeners, that's nothing. that has no information in it whatsoever. So we want to generate something from nothing, and this is why we start from noise. And noise also has another interesting property, is that it has some kind of distribution to it. You can sample from noise. You can't have like a mean standard deviation of 0 and 1 of like a Gaussian of noise. And that's also helpful because we really don't want to sample from every possible space and every possible starting point. We want to be able to sample from some kind of starting point. Do you think it's clear?
It is, but I'm leaning forward in anticipation. So okay, so noise is the true nothing, and it's the basis for what will become something. So in the case of stable diffusion, the model, do I understand correctly that part of the generation process is you start with noise, and somewhere in here, a prompt plays a role where the model tries to detect like features in the noise and makes those signals stronger? Or like I'm curious about, so your explanation of noise being the true nothing and noise having features that can be sort of pulled in, so to speak, is clear, but I'm wondering, where does it go from there to generating something?
Yeah, so that's a natural progression. So we start from nothing and we want to get to an image. So the naive way of thinking about it is, why not like train AI, like some kind of architecture, inject noise, just initialize some kind of like vector or image with noise, and not even give it information, just at the other end give it natural images that it should try to mimic, then try to train it like this, like millions of iterations, tens of millions of iterations. And what you would expect that should happen is that at some point the model should be able to generate natural looking images. And it's still not guided. It's important to say, like, guidance, what you're thinking about, like injecting a prompt, this is already like new age revolutionary thing. Like, let's
Right.
guide the generation. But
So
even
if we go back to like machine learning 101, there's an input layer, there's a bunch of hidden layers, and then there's the output, so to speak. And
Yeah.
what I'm hearing from you is the input layer would be noise, and the label or the expected output is like a finished image. And you sort of have the machine learning algorithm go like figure out how to turn this into that.
Yeah, and we don't, like, at this moment, we're even like modest and humble and say, like, I don't even want to guide it. I just want to be able to generate some kind of like natural looking image, anything that looks like it's real. And guidance came later. But even this, even generating something that looks natural, was impossible to do. And it was like going directly from noise to image, not even guided, just something that looks natural.
Right.
And there were architectures before diffusion called GANs, generative adversarial networks, and they just had a lot of problem. People weren't able to train them. People weren't able to optimize them. And that's an important thing to know about AI in general, that things should theoretically work. Like, there's no reason, like, the task is formulated well. We give the input, we give the ground truth, the labels, and it should work. But numerically, like technically, it just doesn't converge. The optimization doesn't work. And this is why these tricks of how to think about it in a different, maybe gradual way sometimes helps. But I think it's important to know that all these kind of like architectures that develop, they're like a workaround that is kind of like able to do it in some kind of way, but it's not that this is how it has to be.
Right. Why did the GAN architecture ultimately not work? Was it just that there was no convergence in the end between the inputs and the labels? Why, you know what I mean? Like, I'm trying to understand. So there's been many architectures over time. GAN was one of them, and now, you know, the trendy one is transformers. Why did one not work, and why does transformers work so much better than the other architectures? And maybe this is like a separate rabbit hole that we don't go down yet, but you said it didn't work, and I'm curious why.
Yeah, so we already at this moment can make an important distinction between method and architecture. GAN is not just an architecture, it's a method. The method of GANs, adversarial networks, is that in order to be able to do it, we have one network that is trying to generate something that looks real. And there is another network that is a discriminator that tries to say whether this is real or not. So they're kind of like fighting each other. They're training in parallel.
And they're adversaries.
Yeah, because you can't really define in a quantitative way what is real and what is not, right? How much of a distance between, like how much can I distort my images until you will be able to say this is not a real image.
Right.
So the smarter way to do it is like let another network learn between real and not real. And then if this generative model will be able to fool the discriminator model, then we have something that is working well. And the reason I said that it's not about transformer, that even if you would take this new transformer architecture and you would put it in this regime of transformer generator and transformer discriminator, it would still fail.
Interesting.
So it's not about the architecture, it's about the method. And this specific method had a problem that was called mode collapse, which means that this generative model, it's kind of like always went in some kind of minimum in the optimization scheme of something that is easy to predict, but really hard to get out from. So for example, maybe it would generate only flowers because there are many flowers in the data set. And it was like a good point in terms of the optimization to always fool the discriminator, because the generative model said like, okay, if I'm outputting flowers, I'm like a very good flower generator, I always win. But you need to be able to encourage the model to try other things and to fool the discriminator also with trees and also with people, but it's too hard, so the generative model always outputs something that it manages to do. So you have a mode collapse where you're not really interesting, you're generating like not interesting stuff.
Is this where guidance can help?
This is the guidance really comes into play in diffusion, the method that we'll get into, because there you have more chances to intervene in the process because it's longer. But theoretically, yes, you could also do this in GANs. It just wasn't as popular back then.
Interesting. Okay, so GANs died in this really awesome contextual history lesson. Thank you so much. And a new both mode or method and architecture emerged. Is that diffusion? Is diffusion the successor method to GANs?
There was another one in the middle called VQGAN.
Oh.
That it's worth to mention. Like there were really nice results at the moment, and I don't think it would be a little bit confusing to say what it did, but VQ turns to vector quantized. So they kind of like quantized the space a little bit to make things more manageable.
Can we define real quick, as terse as possible, what it means to quantize a vector?
Oof.
If we can't, it's okay. The listeners will type it into ChatGPT.
No. Maybe it's my fault that I'm always trying to find like metaphors that would be like more intuitive. But for example, RGB space is a quantization of real color space. So when you look in your eye at something, you see like true color. But even your eye has some kind of a resolution to it. But when you look at the screen, you only have like from 0 to 255 like shades of green. This is quantization. We took something continuous and we forced it into 255 bins. And we say this quantization is good enough because for practical reasons, it's enough to separate the differences. The same can be done in complicated spaces inside AI. So AI, for example, the weights inside, the numbers that it learns inside can range to continuous, like in float 64, and like huge precision. But in practical terms, when you look at the actual numbers that is needed by the network to do its computation, you can maybe discover that you can reach the same qualities like with half of that precision level, of the numerical precision level. And that allows you to be lighter in terms of like the weight size. You can cut it in half. You need half the numbers to describe the numbers. And also the computation. In modern architecture, you need half of the flops to do the computation, and it can run much faster. And there are different precision levels, floating point 64, 32, 16,
Okay.
and others.
So it's a compression technique where you just convert like a very high dimensional vector into a more compact representation of the vector so that you can compute it more efficiently.
You can say that, yeah.
Okay.
You can say
Perfect.
that.
Excellent. Thank you. Sorry, I didn't mean to go the rabbit hole. So you were talking about VQ GANs, and they were just vector quantized GANs, which yielded like better results.
And now we come into, I think we can start to go into diffusion, but even here, I want to like give a small history lesson about machine learning and AI. It almost always the case that when we try to formulate a task, like in the purest form, let's say even object detection, like here's an image of something, and where's the person? Like draw a bounding box around the person. It's almost always the case that it fails, that the AI isn't able to learn. It's true to this day, by the way, for detection. Something goes wrong. There's not enough signal. We can talk a little bit more about it in the future. It's not able to converge. The numbers are diverging all the time. When this happens, like human constraints on the process come into play, and the ingenuity of researchers and engineers to guide this learning process can really like make things possible. So, for example, in object detection, the first architecture that was able to do it like really nicely was faster RCNN, something like that. So the idea there was to separate the process into two stages. One, like just find objects, like proposals to objects, something that could be an object. And then another stage of let's try to classify whether this is really something that we are interested or not. So one network only needed to look at like contours and like blobs of stuff. And they proposed bounding boxes. Most of them were garbage, but at least they kind of like thought this like HD images that has a lot of pixels in it and said like, all of these don't matter, focus just on these squares. And then the next network looked only on those patches. And now it's like an easier classification problem. Like, is this patch something or not? Or if from the classes that I'm interested in. And all of a sudden it works. We're able to not only detect objects, but also classify them. So separating these like complicated tasks where the AI gets lost into smaller patches of tasks really helps machine learning. Basically, essentially the same thing now is applied to image generation. We understood that going from nothing to something with GANs, with VQ GANs, it's too hard. The model gets lost. The optimization is too hard. How can we make it easier? How can we guide the model into a process that is easier to learn, easier to optimize? And that's where diffusion comes in. Instead of trying to come directly from noise to image, we're trying to do it like a bit more continuous. Like try to make it a bit less noisy. Try to make a little bit something of that is towards natural image, and that's good enough.
So it's taking smaller steps, smaller iterative steps, as opposed to, hey, here's noise, here's the ground truth, make it. Going from that to something more like here's noise and what? Like here's small features that I expect. And now create it. Is that close? Like I don't know what that would look like practically, to go from an absolute approach like noise to image to something more iterative. Or is this the basis then for diffusion?
No, so this is the idea, and the nice thing here is that you can also like simulate like the true ground truth to each step. So we can actually
Oh,
we can take your image right now, and we can take complete noise, and we can interpolate. We can take half of your image, half of the noise image, and like really half and half, overlay them on top of each other, and this is like half noised Tejas.
interesting.
And going from noise to half noise Tejas is easier than all the little features that you have, the moles and the hair and everything that makes you unique and recognizable by all of your friends. That's an easier intermediate step to reconstruct because, okay, now you have your distinct head shape, right?
Yeah,
And you have your mustache and you have that beard.
yeah,
And but we still don't, and we can try to draw that. It's kind of like an artist making a rough sketch at first. Like
yeah.
this is roughly Tejas. This is Tejas head shape. This is easier to learn compared to all the little features that you have in the skin texture, in the hair texture, in everything, which be
Right.
very hard to learn.
Yeah. Interesting. Okay, so it's going from this distinction of noise to partial noise, partial truth, incrementally to the point where it's fully denoised truth, is so key that you make this distinction. Because like my naive, noob, inexperienced mind was thinking as an iterative approach to do it the old feature detection way. I don't know if this is even old, but previously you would have like a matrix of color value, a black and white image, like 0 to 1 of like, black or white, and go like section by section of image. You know what I mean? Like in little blocks. And so when you say no, it's the whole image, but from noise to slightly less noise to slightly less noise, that distinction becomes so much more clear to me. So I appreciate you saying that.
Yeah, but your intuition is not that off at all. You're just confuse the architecture. You confuse the
Yes.
method. Because
Yes.
autoregressive, there's also autoregressive image generation. So the people are trying to take the GPT method of like next token prediction. So in GPT and ChatGPT, you try to output a word and then you kind of like build on top of that word by word. There is no reason that we can't do it for images. So we start
Interesting.
from the top left,
Yeah.
and then we try to generate like this green background that you have, and then we go
Yeah.
another layer down, and then we have the top of Tejas. Okay, now we need to go to a little bit further, and we can theoretically in ChatGPT like way, instead of words, start to pixelate you.
Interesting.
And it actually works. It just works a little bit worse than diffusion and flow matching these days, but it is a viable approach, and it implements what we talked about of like doing this a bit incrementally. Like I can't generate Tejas in one go, but maybe I can piece it like piece by piece and think about it, and I will be able to construct something
Interesting. And
eventually.
this is also why, man, it makes so much sense now that diffusion models output images that are so smooth. You know what I mean? Like the mid-journey look, the DALI look. Like it's smoother than real life. It looks like a painting because the denoise process goes too far. Do I understand that correctly?
It's not that it goes too far, but there is only very, very, very little steps in that training regime where I just noise you a little bit. Like you can even look at your image. Sorry that I'm always referring to your image, but
It's fine.
it's like this is it. This is what we're trying to do. Like
Yeah.
even here, you have some kind of pixelization, right? And this is from compression. What's the video encoder
Yeah.
is doing here? You have some kind of like pixelization, and and some images can have natural noise from maybe sunlight or something like that, or smudges on the camera, and it's part of what you train on.
Yeah.
So when the model during training goes into that regime, what probably happens is that you really can't discern between those fine features that are really part of your skin and something that could have come from an Instagram filter of kind of like something retro, or something that came from a bad camera, or something that came from the sun.
Right.
So
Or something that's just noise from the initial input.
Exactly,
Yeah,
exactly. Or
interesting.
something that we really noised right now. There's just not enough information. So what AI does, it's kind of like an averaging machine in the end. It's kind of like a mean machine. And it says like, okay, like if I try to predict that, then I mostly fail. And then I'm just going to take some kind of like average, and that's the smoothing.
Interesting. So models today can't really tell noise from noise, if you know what I mean. Like you can't say, hey, this noise is better than that noise in a sense.
Yeah, yeah. Life is
Okay.
noisy. Life is noisy. Like real life is noisy. So you can't like unless when images step into the 4K domain. It's
Yeah.
starting a little bit right now when you have this like 4K Ultra HD crisp images where you can see the pores in your skin.
Yeah.
Then maybe there would be enough signal there to understand whether this is like a really pore from the skin or noise from the noising process.
Right, because it's just the sheer number of pixels. There's so much volume that you can tell. Interest is this. So this sounds this what we're talking about here is the diffusion method, right? The technique.
Yeah, and you noticed we haven't even talked about latent space.
Yeah, but I'm so interested in diffusion now, and thank you, man. You're like the way I'm gonna make a metaphor here. It probably won't work, but whatever. The way a really great diffusion model can separate features from noise. You're separating my mixing of concepts, diffusion and latent space. So I appreciate that. And I'm really into this diffusion topic now because it explains so much of the creative generation process. So I use Suno sometimes for music. It's just I'm assuming this model was created from here's a bunch of audio noise, here's the ground truth with less noise but still a bit noisy, and it went on that way. So that's
Yeah,
audio. With fashion, you're probably doing the same thing with photos of clothes and video. Sora probably so like across modalities, this is the way to generate stuff.
yeah, yeah.
Wow.
And by the way, it doesn't have to be noise. Doesn't have to be. For
But you said noise is
example,
the true nothing.
yeah, but this is when you want to do something like really pure, like generate something from nothing. There are other use cases. For example, colorization. If you want to have a nice app that starts from a black and white image and then colorizes it, you don't really have to start
Whoa.
from noise. Just
Yeah.
take all your data set, transform everything to black and white. And now you're trying to learn from black and white to color. So this is hard to do from start to finish, but you can take like half a saturation, quarter saturation, 90% saturation, and then you can gradually learn how to color the image, and that would be a better and way to learn how to do it. And that's really the state of the art method of colorizing today.
Wow. I so like all of what we talked about for the past like half hour from sort of starting in messy territory with latent space, but then going from like GANs to VQ GANs to diffusion, all of this brings AI to life in a way that it hasn't been previously to me, and I'm sure many of the listeners. So that is so cool. Okay, so the basis of all modalities really with diffusion is this. Does this also translate to text or not? Because like, what is noise in the text domain? Just like random characters?
Yeah, I know that there's diffusion for text. I'm not an expert in that field. Unfortunately, all my life I've been strictly in the computer vision domain. So like I live and breathe pixels, but not text. And yeah, we can talk about how it relates to fashion later, just because we insisted on not using text for virtual
Yeah.
try-on. So this kind of like makes us unique. Like we don't like text. But
Does wait? So do other virtual try-on platforms use text somehow?
they are usually leveraging the text to image models. And so they
Oh,
usually either have to supplement the try-on process with a prompt, just kind of like to help to guide the virtual try-on. Like they have an image of the dress, but you would also have to type like this is a woman wearing a black
interesting.
dress. Or they would use the features in some way and use some kind of like image to text adapter and stuff like that. But we can focus on that later because it's getting into the guidance domain that we haven't talked about yet. But see like how much there's talk about before you get into spaces and guidance and stuff.
Yeah. Yeah. Okay. So I think now we have a decent. I mean, you be the judge, but it seems like we have a decent understanding together of diffusion models. What's the next step? At some point, we need to arrive at latent space. I feel like
We
you're better at navigating this than I am.
Yeah, so we can get into latent space. So it's really important to know, for example, that latent space is not inherently a part of diffusion at all. It's a technique. So we talked about diffusion, we talked about how doing it and everything. We could have done it specifically in pixel space. The thing is that the process that we talked about of gradually noising the image and finding this intermediate, even in pixel space, it's still hard to do. Even then, researchers were able to do it in like 32 by 32 pixel images, 64 by 64 pixel images. They haven't been able to crack those like high definition images. It was still really hard. And the difficulty comes, now we can delve a little bit deeper into machine learning concepts in like the loss function.
You said delve. Are you an AI? I'm totally joking. Okay, so the loss function.
Yeah, so a brief introduction to the loss function, I guess, is necessary. A loss function is basically the ultimate quantitative measure that helps us guide the learning process. So no matter how it's kind of like magical, but no matter how complicated the process is, detecting people, classifying cats, generating people, at the end, it's only like one number, like one score number that has to say, is it good or not? So in what would be, for example, your intuition about what's a good image? Like how would you measure quantitatively whether I constructed the image well or not?
Does it reflect what I want? You know, I mean, I can't think of, yeah.
It has to be like one it has to be a number. So you have to do so. You have the image that you generated.
Yeah.
And you have the real image. And now you have to do some kind of operation between them to say whether this is a good match or not.
If it's a black and white image, then it probably equality based on, pixel position of 0 to 1, black and white.
Yeah.
And then sum that and be like, does this, how close is it? That would be my intuition.
It's good. You just take the images, subtract them, pixel level. If it's the same values at all position, it's a perfect image, right? So if it's 0, then it means that all pixels are exactly in the same space, exactly the same values. It's perfect. And it's actually what's done in diffusion. So there is there's nuances to it. For example, you can predict either the image and then subtract the image. You can also do a trick to predict the noise instead of the image, because it's equivalent. Like if you see an image that is half noised, then predicting the image or predicting the noise is the same. It's just what part of the equation did you predict? It tells you what then the other part is. And there are also other tricks that we can go into, which are a little bit of more advanced, that you can do some kind of interpolation between them. Or, for example, the newest trick is to do flow matching. We can get into that, but it's basically the same. Like the intuition of just taking two images and subtracting them and getting 0 is perfectly fine, and people still do it.
And in some cases, this isn't enough, and so they resort to these advanced topics that you're talking about.
Yeah, and also in this domain, like bringing us closer to latent space, we can start to talk about like signal to noise ratio, or kind of like the strength of the signal for the training process. So if we try to generate ourselves, like our images right here on the video, and we're trying to generate, like, let's generate Tejas and let's generate Dan. We are about 50% of the images in terms of like pixel.
Yeah.
Okay. So if I tell you I want to generate Dan, then even if I get my face right, I still have 60 to 70% of the images that I didn't give you any guidance for. And you can generate whatever you want, and you'll probably make a mistake. So the model needs to be able to learn that from what it did right in the face, still have enough kind of like signal between what it did wrong in all the other stuff that it couldn't have possibly known. What would be my background? So it's a noisy process, because all kinds. Like if you want to generate a cat, there are so many ways to generate a cat. And if the cat is only 10% of the image and you're in pixel space, then the signal of what you did right compared to the something that you couldn't have possibly matched correctly with the ground truth image is just too large. And this is why pixel space generation is really, the higher you go in resolution, it's not about compute. It's not about the intensity of compute, although it is a factor. It's the signal of what we're trying to learn here is too widespread across pixels. Now we're in latent space. So latent space allows us to take these RGB images of these HD images, compress them to a pixel space that is much richer, into a dimension that is much richer in information. So if you be able to do predict features there in this latent space, it would have a much stronger signal, because things like background and solid spaces and areas, they're not really fundamental there. They're not really interesting there. They don't carry a lot of signal there. So it allows you to do two things. It allows you to take a high quality image, let's say 1024 by 1024, compress it down to 128 by a factor of 8. So you're already working on much less features.
Space, yeah.
Yeah, space. And each, let's say square there, I still say pixels. I hope I'm not confusing anybody, because it's still, when I see like a 2D arrangement of something, it's still pixels in my head. But it's much more information rich there. And it basically, it was a huge discovery. It was a huge discovery by the team that released Stable Diffusion, that said, hey, let's stop working in pixel space. It's really hard. And there's a lot of redundant thing here that makes it really hard to learn. Let's take images and compress them with, I will get into what's this compressor, what it does, and compress all the images to this latent space, and try and even noise, all the noise is here in this latent space, and try to do the denoising process, this interpolation process in this latent space. And even the output of the model is still in the latent space.
Wow.
And now comes the next part of the encoder, the variational autoencoder. It now decodes what the diffusion model generated back into the pixel space.
Wow. Okay.
So it's like much more condensed, much more condensed.
So I understand. This is so great, Dan. I just need to, like, as an aside, be like, wow, you are a true master of your craft, because the fluency with which you're explaining this is absolutely bananas. And I think a testament to how good it is it's actually like landing with me. Which, you know, I'm known to be somewhat dense, so this is good. So to contrast pixel space and latent space,
dense is good in computer vision. Dense is exactly what you want. Dense vectors, information rich. You don't want all this sparsity.
Fantastic. I appreciate that. Thank you. Yeah. So pixel space is just massive. Like for a small image, like, I don't know, like 150 width and height, somewhere around like 25,000 dimensions, high dimensionality, which is too expensive to perform these processes of deriving features from noise, etc. And so a team of researchers said, hey, what if instead of pixel space, which is too big and complex, we encode an image into a much smaller latent space, do all these operations there. The model even outputs just a very smaller latent space artifact. And then there's a decoder at the end of it that says, okay, cool, it just reverses that encoding algorithm to give you an image. Does that accurately capture? Oh, wow.
Exactly
cool.
right.
Okay.
Yeah.
So the latent space is just a lower quality representation, or quality, maybe not the right word, but you get the idea. It's a compressed representation of a very high dimensionality space. Interesting.
Exactly, yeah. So what's important to understand also that this, now we can talk about this encoder decoder, this VAE, variational autoencoder, that it's completely detached from the diffusion architecture. It's like an extension on top of it.
Right.
It's not part of the core of the method. It's just a really, really nice trick. And it's trained separately. This is its own AI. It's in its own AI model that has its own task, that is to reconstruct the image. So what an autoencoder does, in principle, any kind of autoencoder, you take an image in the input, and with AI, and also you can choose any architecture, the architecture doesn't matter, you try to compress it to a lower space. So practically here, we take an image that is 2000 by 2000. We try to compress it to 200 by 200, so by a factor of 10. So it would be kind of like the same image, just with 10 times less pixels.
Yeah.
And now the next phase of this network is to go from this compressed middle bottleneck back to the original image. And the loss function is the same. We take what we inputted at first, we take what we outputted at the end, now we compare. And what we want this model to do is to be able to go through that bottleneck and come back and to have almost no information loss at all. So the AI needs to learn like really good features that it can extract from this input image, such that it will be able to reconstruct it almost perfectly on the other side. And it turns out that you can do it because pixel space is really redundant. There's a lot of stuff that is easier to arrange for our computers and our eyes, but in terms of information, you don't need all of this information arranged in pixels.
Interesting. So these VAEs are just, in a way, functions. Functions that compress images. Like, if I think of a highly compressed image, ultimately I think of like 8-bit, like Sega and graphics, right? Like these highly pixelated characters that fight in like Street Fighter and stuff. So what I'm hearing is, if we wanted to like give me a face swap or a deep fake of me being Brad Pitt or something with a diffusion model, then we would actually like take this photo of me or this video of me, break it down into something extremely low resolution, like a Sega game, where it's like highly pixelated me, but there's still enough information there to swap my face in this very sort of low resolution space, and then decode it at the end to get back a higher resolution result.
Yeah,
Crazy.
It's all a matter of whether you can come back. This is kind of like what's the key thing here. Are you able to come back from that compressed state in a way that is almost lossless?
So this sounds almost like, and so, I think the naive way of thinking about these VAEs, and I guess VADs, is they're just functions with rules that engineers write out, but this is probably not true, right? They're probably their own models to encode and decode, because I have to assume like the rules, so to speak, of encoding and decoding high quality like pixel space images are not so easy to just write, like a human writing an algorithm.
That's the thing. So human writers, they did like JPEG and WebP. This is kind of like the human engineering. And the thing with these methods is that when you do this wavelet decomposition, you decompose the image in a way that still contains the same amount of bits.
Right.
Okay. But it's rearranged in such a way that you can discard all those high frequency features, such that your human eye in our computer screens won't be able to tell the difference between before and after. But in these algorithms, it was discarded and you can't come back. You compress the image, it's virtually indistinguishable from what it was before, but you really can't come back. You threw away that extra information that you decided to leave. What you are able to do with VAEs to some extent, that you can't come back. You compress the image to something that is much more space efficient, much more information dense per kind of like pixel, per dimensional space, but you are able to expand the image back to the original space with some degree of information loss, but very good. And this is, by the way, another factor of the smoothness. This is another artifact, because those these like textures, like this really, really fine textures, they get lost in this compression. If you do it directly in pixel space, the texture is a little bit better.
Okay, so what it's going to take to get out of the uncanny valley is to get enough compute, probably, where these operations are just possible in pixel space without VAEs.
Yeah, but still there is a matter of like what we talked about before, like the original cause of that. Like the images also need to be flawless. If your
Right.
images are noisy, your model wouldn't be able to tell the difference between noise. But theoretically, if your images are perfect and they don't have a speck of noise in them, then yes, you should be theoretically able to reconstruct every texture.
But what if the images are not, noiseless, but they have sort of the right noise? Is there such a thing where there's like a degree of correct noise that helps our human eyes see things as lifelike and not uncanny valley? Does that make sense at all? Like we sort of associate a certain level of noisiness with, okay, this is what the world looks like, and we don't see the world without noise.
Yeah, it's actually interesting. You're right, because there may come an age where it looks too real. It's kind of like the
Yeah,
soap
exactly.
opera effect, like the soap opera effect
Exactly.
that people hate. That it's like it's too smooth, it's too HD, and people like this is not real life. This is something like completely like ultra aesthetic, and it could happen. You're right. There is a measure of natural noise that would make
So
an
then we
image
need
seem, yeah.
Yeah, so then we need models to get really good at identifying like good noise versus bad noise. Oh, okay. This is
Yeah.
so cool, man. I have such an appreciation. So it sounds like there's actually teams of researchers working on exactly this problem now. Like, how do we get out of the uncanny valley? Is there work that can be done to do that? So cool. You've explained this so clearly, and that's probably because, right, the work you're doing in fashion, y'all trained your own model, and it's an image. You mentioned earlier, like you're allergic to text, so it's an image to image model. There is no textual guidance. How does that work? So I'm assuming you're not starting from like just noise. You're starting from clothes, or you know what? So for those listening who maybe haven't used fashion, I think it's worth just spending a little time explaining how. So I've used it. Great product, love it. You choose clothes, a picture of clothes, and then you add a picture of yourself wearing literally anything, or nothing. I don't know if it works with nothing, but and you hit a button and it shows you with those clothes on. But I've also seen you use like not people, so like AI generated people as well that you put in these clothes. And there was a cool Christmas sweater with Satya Nadella in a Christmas sweater. So there's all these cool things. How does that work in the context of all the things we've spoken about today? Specifically, do you start from noise, or do you somehow start from the clothing item? I guess that's a good like jumping off point, and then we can probably go deeper into the fashion way of building.
Yeah. We, as an intro to this, I think first something that we haven't talked about at all is guidance.
Oh, like
So,
prompts.
yeah, for example, but guidance is like it's a general topic. Up until now, we talked about like pure image generation. We haven't
Yes.
talked about guiding that process. And
So
and
so
to
so
be
with fashion, guidance takes the form of like, here's the sweater, and you
exactly.
guide. Okay, got you.
Exactly. But after everything that we talked about, I think guidance is not such a complicated addition to this process. So you before we said, take this noise input, generate some kind of image. The only criteria here is that it would look natural. It would look something from our data set. The next step is don't generate any image. Like what researchers did before, generate some kind of like class, some kind of like category. So they said like, I want to generate a lion. I wanted to generate a plant. I wanted to generate a car. And what you usually do is not that complicated. You just have to represent this category in some kind of feature. So it can be some like 1,000 numbers long vector that represents a category. You can learn it, or you can give it in advance from some other model that is good at extracting features. And then you inject it in some way into the architecture that the model can look at this vector of features. So while it looks at the noise, it also said, okay, this is the noise, but I also have this external information that I can compute in some way into my features. And when you train it long enough in this like reference, you are able to guide the process into a specific category. And prompt is the same way. You take a text, and we have text encoders. And you can take a very long text, but at the end, you can still represent it as features. And this is the first time where the transformer architecture is really powerful compared to before, because up until now, we didn't even need transformers. But the only thing that you need to know at the moment about transformers is that you're able to compute a sequence. You're able to analyze a sequence of features. This is kind of like the powerful thing about transformers. And in text, it's really useful because you can't represent a whole sentence with just one vector. Like you can represent a category with one vector, but in a sentence, the order matters. And the words, it can change the context. So you want to keep it separate and then work with the kind of like original structure. And that allows you to analyze a sentence. But with images in fashion, it's the same. You just, instead of text, instead of category, you need to represent in some way an image and give it to the diffusion model in some kind of form. So let's say, again, tokens that represent patches of the image. And then it acts like kind of like as a reference to what kind of image are we going to.
So it's an image to image model. Do I understand then correctly that they're in a way, and I'm probably going to get this wrong, which I embrace, in a way that there's really at least two inputs to the model. One is just noise, and the other is your vector or your tokens for your like sweater that you want to come out of the noise, so to speak.
Yeah, it's exactly right. There's three actually that is important. There's actually even more, but the core for virtual try-on is at least three, because you need the noise, you need the reference, like you said, but you also need the original person. Otherwise,
sure.
Otherwise, you lose it. You have to keep it also in the process, and everything needs to kind of like mix together in the feature space inside the transformer in a nice way, so everything will blend together nicely.
And do I understand correctly that nobody knows how exactly that happened? Like a lot of people say these models are just a big black box, and you like no human can look at those weights and go, I know exactly how it's doing this.
I can't say that I know exactly how it does it, but I do understand that at least in virtual try-on, it's less mysterious compared to, I would say, text to image, because at the end of the day, virtual try-on, it's a very sophisticated warper. And warping is something that you're also able to do classically, like Photoshop. In Photoshop, you can create a smart object, and you're able to do something, and it kind of like it will have some like a matrix of morphological transformation. It will be able to warp it, but then you have to handcraft the warping grid to make it perfect. So the only thing, like in principle, that we're doing here is that we're automating the process of learning these warping grids on a person. And there is some kind of like generative effect because mainly because of the difference of the clothes. So if a person wearing a coat and you want to replace the coat with a t-shirt, it's not enough to just do warping grids like in Photoshop. You have to remove the coat and then understand what should be kind of like the template of the t-shirt on a person, and then you can start to warp the features and the details onto the person. So there's a few extra steps there that the model does have to do kind of like magically, I would say, generating something from nothing. But at the core, it's an automated machine to learn warping fields.
Awesome. Can we talk a little bit more about guidance? Because it's not clear to me how, you give these vectors to your model is input of like, a clothing item and the person. How does that even work? Like, okay, let's assume it's like programming code and you're passing in like input arguments to a function. In the case of then reconstructing this input sweater from noise, how does that work? Like, how does
It's hard.
how does the model like know to get those features out of diffusion?
So this is the first time where transformer really kicks in. Like we haven't talked about architecture at all until now, and it really wasn't important because an architecture is just some kind of like cool layers that are able to run operations in some set of restrictions, and those operations are learnable in a way that can help learn any kind of task. But you could do it with convolutions. We haven't talked about convolutions, but it's also ConvNet and convolutional neural networks. It's also a way to learn image features. But here specifically, we do need the transformer because transformer has this attention mechanism that probably everybody heard about it for now. And about guidance, I think the most intuitive place to start would be not from this domain, but the original domain where attention was invented, which is translation. So even before transformers, this attention operator came in, I think it was a Google paper of machine translation. Before transforming, there were something called RNNs, recurrent neural networks. It was also an autoregressive architecture that also outputted tokens. It was the same concept time by time again. And in machine translation, you first process for example, the English sentence, and then you need to output the German sentence. And in that paper, they showed for the first time that it doesn't make sense when I need to generate the first word in my translated German sentence, it doesn't make sense to look at the entire English sentence. There are some words which are more important to look at right now. So they invented this attention operator, which is like English and German are different, right? But in feature space, they're not supposed to be. That's kind of like the neat trick here. Like dog in English and dog in German, the inputs are different, but in this feature space, they are supposed to be the same. They have the same meaning. So we look at the outputs from one network and the outputs from the other network. The text is different, but we try to see what are the similar vectors between what we did. So if we're talking about dog right now, there should be dog somewhere in the original features that I can kind of like calculate the similarity between them and say like this is what is important right now and take the features related to this specific word. And this is guidance in its first form. Like we are trying to generate a sentence with the guidance of the English sentence. And we're using this attention operator to know what we should look at this moment to incorporate into our current generation.
Right, but for this you need vectors for dog in English and dog in German. And these vectors have to like probably not have that much distance between them because they mean the same thing, just with different like tokens, so to speak.
And that's exactly what the model should learn. When you put that attention operator inside, the model learns this similarity inherently because it's incentivized to make it similar, so it would be easier to guide through it. Yeah, these AIs are really. This is why you can't really say you can have some kind of intuition, you can have some kind of like idea about what's going on, but it's really complicated. It's really magical that these things work.
Right, because the vectors themselves are generated by another model, an embeddings model, as far as I know, or an embeddings layer. And we talked earlier about VAEs also just being models that output like encoded and decodable versions of pixel space. So then do I understand correctly that like when we talk about transformers architecture or other architectures like the VAE architecture earlier, like all of this is really just stacking models towards a specific outcome. You know what I mean? Because like if we talk about the translation architecture or model that uses transformers, what's happening is you get an English input dog that then becomes vectors. Some vector, some embedding layer does this, or embedding model does this. You get vectors. You compare the vectors, or at least the model compares the vectors and learns that this vector in English close to that vector in German, therefore probably this token in German. Is that an accurate representation of architecture? Is like a stack of different models slash layers?
Yeah, like let's look at diffusion, stable diffusion, like even the new one, 3. It's
Right.
you have the core diffusion models, but you have the VAE encoder and decoder as kind of like first step and last step, and you
Right.
also have all the text encoders, and I think they use 3. I don't remember. They use Clip, they use the T5 XXL from Google, and I think they're using another one. I don't remember, but they're using 3 different text encoder which are pre-trained that encode the prompt, just because each text encoder kind of like gives another flavor to the model. And so they actually use all of them and then inject it into the model. So these are 4 pre-trained models just stacked as information givers to the diffusion, just as external context.
Wow. So it is just stacking models on models, and somewhere in there you have your own custom model logic. Like even with fashion, you've got your own like image to image model that you've trained. But when we talk about architecture, it's just that it's like stacking models towards like an appropriate output.
Yeah, and you can do, for
Wow.
example, have you heard about control nets?
I I haven't.
No, it's okay. It's another layer inside the diffusion models, but for the diffusion models have some kind of like extensions that are called control nets, where you can add additional inputs, for example, like body pose. So maybe you've seen this kind of like skeletal body
Yeah.
poses.
Mm-hmm.
So you can also use that as guidance. If you want to generate a person at a specific pose, you can fine-tune these stable diffusion models with this pose image. So this pose information would be able to guide the pose of the generated person. And
Interesting.
this is also a pre-trained model, and people are doing it with depth maps. People are doing it with even Canny threshold, like edges detector. You can basically, this is why you can really think of anything of how to
Wow.
guide the generation model, and you're using the pre-trained stack to do it.
Is this what you're using at Fashion to get your like models in specific poses? And also, I see y'all are doing video now as well, and those models they do model poses. Is that
So,
part of what you're doing?
so for example, pose is something that we do incorporate into our architectures. Yeah, because even if the model, for example, the person that you input, if you have to transform them significantly, like for example, someone that wears a coat and now you need to put a t-shirt on them, intermediate step could be to remove the entire coat. And that doesn't leave a lot of terms of like the skeleton of the person. So a pose model can kind of like help uh, draw the base of how this person is positioned, to help guide the model put the t-shirt on them in a good perspective.
Interesting. That's so cool. You know, you're sort of giving me ideas for. I've always wanted to build an application that using PoseNet will tell you how you're doing exercise. Like it'll watch you like a camera that watches you like lift weights and will tell you like is your form good? Is it
I
not? Are
think
you
I think
lifting?
I think I saw some demos of that. Like people are doing it. Yeah.
That's so cool. Yeah, I would actually pay for that because I want to
Mm-hmm.
know, you know, like when I'm bench pressing, like when I hit failure, like by a machine telling me, not how it feels, you know. In any case, awesome. I think we have such a good understanding of all of this, but I have maybe a fundamental question. Like if I wanted to train a diffusion model, kind of like what you have at, or not me, but like the listeners, right? If people want to play now, because I feel like now we know the tools, we know the concepts, we know the terminology, we've covered a lot of ground, and I'm guessing at this point somebody's thinking, oh, I want to get my hands dirty. I think we all know on a surface level that this stuff is very compute intensive and expensive. For the reason being, it's really just like a big loop of calculations that need to happen in parallel, and GPUs give people the possibility to run operations like with very, very high parallelism, right? And so it can maybe, and correct me if I'm wrong, but it could probably happen on non-GPUs that would just be very slow and maybe like occupy way too much compute that doesn't leave room for the kernel to do its job and then crash the system. But I'm trying to, I guess the question I'm trying to ask is how can people play with this and why are the constraints what they are?
Well, first of all, the good news, and this is basically what everybody's are leveraging right now, is that you have these open source foundational models, which already had kind of like the big heavy lifting of the compute baked into them. And the concept of fine tuning, to those that maybe don't know, is that AIs, once they're trained sufficiently, they become very good feature extractors. So the terminology feature extraction is very powerful. Even Stable Diffusion itself is leveraging these text encoders because they are really good feature extraction from text. So even Stable Diffusion is not trying to train everything from scratch. The VAE is also a very good feature. This compression, you can also translate it into feature extraction. You take the original image, you extract what's important there, and you work on these condensed features. Okay? The ability to extract good features is key. This is the hardest thing when you train AI, because you start from randomness, you start from noise, even in the weights. This concept also applies to the initial state of the network. At first, it's noise. And then during training, you come from random computation into something that is extracting meaningful data information from the inputs. And from that point, it's easier to go and let's say, for example, if you have a very, very good cat classifier, then going from cat classifier to dog classifier is not it's not such a big leap than like random noise. Like, okay, now we need to adjust a little bit how ears look like, a little bit how the face looks like, but still everything about the fur, about the context is the same. So you're able to leverage these open source models to a very high extent. And this is what people are using. So, for example, all of the LoRa industry. Have you heard the term LoRa? Yeah, so...
LoRa meaning low ranking adaptations.
Exactly, yeah. So there's huge businesses built on top of it. People, all the applications of personalized photo shoot generations and personalized headshots, all like people are having tons of users creating cool applications, and at the core, it's having like a very, very tiny adaptation to a specific like face or person, or even e-commerce, it could be products, and kind of like intervening with the current very, very well-established logic of feature extraction and just adding like a few bit of fine-tunes to the logic to be able to generate specific faces or specific products.
Is that computationally expensive? And it does, just so I understand, that does require like changing the model weights to get a new model, a specialized model for a specific face or adaptation.
So not exactly. That's the trick with LoRa. So the trick with LoRa is that you don't modify the original weights at all. You do this kind of like little in between. You put a little in between delta functions that take what a layer outputs and then does a small modification to it before it passes it over to the next layer. Yeah. Okay. So what you're actively training are only these like little adaptations. So it's not that computationally expensive, because the gradient, this is a small technical term, but what makes optimization so difficult and compute heavy and memory heavy is that optimization happens through backpropagation. And that is a term that you have to remember all the gradients of the operation for the entire network. And if you're doing that to a 20 billion parameter model, you need to have a huge memory capacity. Right. But when you're using the model as is, You don't have to remember anything. You're just using the output. You can forget what happened. And you just need to remember the gradients for these little things that you attached. That becomes much more computationally affordable, and this is why you can do fine tunes in 30 minutes, nothing more. I'm not saying that everybody could do it on their personal MacBooks, but you can open like a cheap machine in some kind of a cloud provider for an hour. Requires some kind of like DevOps-ish skills. If ChatGPT can help you, but you can do it there for like $10.
Interesting. So I have done a fine tune on my M1 MacBook Pro, Mistral 7B, so a very small model, doesn't really have much as far as I know. And the problem, I did something wrong because I kept getting like nonsense output, which was very surprising because to me, like exactly what you said, I thought the output, meaning the model is the model, and I'm just like adding like a few small adaptations to it. Turns out like I tried to do some inference with this and I just got like absolute garbage. I'm not sure what happened there. Definitely something wrong, but what's the best resource for people listening to maybe follow up on that, right? Like for example, if I wanted to, so the earliest interaction I've had with any of this was like 2022. I was able to, using Dream Booth, fine-tune Stable Diffusion on my face, and I made a bunch of cool avatars. But to be honest, I didn't really know what I was doing. This was just like a Google Colab notebook, like run these steps, add your images, and magic happens. What was that magic?
So specifically, the original Dream Booth version, it was a full fine tuning. It was before the LoRa trick, but it was still possible because it came about when it was Stable Diffusion 1.5. It was still about 800 million. It still ended in M. It was still million, before billion era.
Wow.
So people could still do a full fine tune in a Google Colab, like you said. So it's a T4, it's a 16 gigabyte VRAM GPU. Once we came into Stable Diffusion XL, which I think is 3.3 billion, then it became impossible to do with 16 gigabytes, but LoRa came to the rescue. And that's it. And about the magic that you talked about, it's basically, it's good engineering. It's just foolproof engineering of guiding you and minimizing the interface for you to not touch anything that you don't need to touch, and giving you the parameters that you need to work with.
Yeah, no, but what I mean is, I mean, I'm thankful that it's good engineering, but what actually happened? You know what I mean? Like, I feel like so you're probably creating LoRa's for fashion customers, I have to assume. Like, if I want to see what I look like, there's adaptations of my face and body.
You mean
that
what?
influence.
How it happened that you were able to generate your face?
Yes, exactly. Or maybe not how it happened back then, because LoRa's are newer than when I did it. But if I was to do it today, right? If I was to take Stable Diffusion XL and fine tune it to output images where I'm the main character, like how would that work?
Yeah. So the assumption that you take when you're doing these fine tunes is what we talked about a little bit earlier, is that the models have very, very rich features, capabilities inside them. So what you're assuming is that this model is able to generate me. So there is no intrinsic limitation to this model's feature, the things that it's able to output, that should constrain it for being able to construct my face. The challenge here is from the all possible range of inputs and outputs that could happen, why would it generate my face? So we're coming back to guidance. We can generate many pictures of a person, but this person needs to look like Tejas. So the idea is that the features are there, the capability is there, the guidance is not there. So what you're doing in Dreamproof in LoRa is just taking, injecting a new keyword, injecting a new prompt. People use some kind of like random strings of number, or like one boy or one girl, just some kind of like trigger keyword, like a safe word. And now you're helping the model associate between this keyword and the images that you fine tune.
Interesting.
And with just these little adjustments, because the model is able to generate these features, you are able to take the intrinsic guidance capabilities towards generating your face. But the capability is there. You're only doing like guidance fine-tuning, not really feature fine-tuning.
Got you. Interesting. Okay, so I associate correct me if I'm wrong. I associate the vector of this special token that represents me with the feature that represents me, aka my uploaded face, and then the model does the rest.
Yeah, you just need to
Oh,
help it guide. Yeah. So where would it fall? If you would want to generate MRI images of tumors, sorry for the bleak analogy, probably it's not there. It's not
right.
there in the, so you probably won't be able to fine tune it with a LoRa because it's not a matter of guidance. It's just the features, the way to construct such a black and white non-natural image is not there. So there you would probably need to do a dream boost, like a full, because you would have to work with new features that aren't there, or like spectrograms, things
Right.
that are not natural images.
Right. Fantastic. Wow. Okay. Final topic. You mentioned earlier that, fashion, I think this discussion has just given me like orders of magnitude more respect for fashion, which I already have, given that y'all are creating your own model, performing your own training and evals and all of this. You mentioned earlier that, GPUs are killing us because of the cost of computation. If somebody wanted to do what you're doing, which is like make their own model for like virtual try, maybe not virtual try, maybe something else, right? Like I don't know, like workout stuff. Is it accessible enough to the vast majority of people? Like, is it fair to say just go like spend, I don't know, like $500, get a machine with a GPU and play? Is that realistic, or are there more barriers to it for the like vast majority of people?
Our case is pretty difficult. So first of all, it is accessible because there are cloud credits. So for example, Azure, shout out to Azure Cloud. They are sponsoring me in some way because they're very generous with the credits package. And for example, our model already spent 100,000 USD in terms of GPU
Wow,
credits.
wild. Is this just for the training, or is it for like all of
Just
the training
training.
inference? Oh my
Just
goodness.
just training. And so to someone like randomly coming in, no, it's not accessible because nobody has 100,000 USD laying around. But there are these cloud programs. They are interested in AI startups. And if you have a cool idea and you have the expertise or some kind of like willingness to show the expertise, you will probably be able to join more and more permissive programs, and you will be able to get these credits. Another thing that is very difficult for fashion is that we are not using pre-trained models. That's a problem. So we aren't able to piggyback on top of what I told you before, that doing these little adaptations to make it work. Believe me, we tried. Everybody tried. And if it was possible, then we wouldn't even be a company, because everybody would try. Like, so many people want this and so many people try this. And if it was possible to fine-tune Flux with some pairs of virtual training samples, then people would have already done it, and it would work, and there was nothing interesting to do here. For various reasons, it's not possible to do it with fine-tuning current available open source models. So we had to eventually train it from scratch. And another thing that we are doing, which is pretty crazy, is that we're not using a VAE. So we're not using compression, which explodes our computation about 8 times more than the parallel model.
So you're training and inferring in pixel space?
Yes.
What?
Yes. It's hard to explain, and there is also some kind of like a secret sauce here that I really can't reveal. But it's my personal conclusion, maybe wrong conclusion, that you can't do virtual try-on in latent space. So to all
Wow.
my competitors out there, then join me and prepare to open your wallet. And maybe it will be possible. Of course, people are brilliant. People are always coming up with new methods, new tricks. But at least at the moment, I have my reasoning to think that it's not possible to do in latent space. And so we are focusing all our research to how to do it in pixel space. And fortunately, there are very good papers out there. It's public knowledge. Brilliant researchers from Google mainly that are always sharing more methods on how to do pixel space training more efficiently. And so we are heavily relying on that. And of course, adding our own touches to the architecture. But it is possible. It's just very difficult.
Interesting. Have you all contributed back any research? I'm curious because like it sounds like you're solving not a unique problem, but the way you're solving it is unique, right? I don't know anyone else doing such work in pixel space. As you mentioned, the other virtual try-on services typically will use text to speech. For example, even like I use some audio AI applications like Suno for sound, and even they will use text to guide the process. It's not like audio to audio. It's not like I just upload like here's some songs I like, make me something that you know. So with that, I assume that you're on a frontier that is pretty sparse, meaning there's not a lot of people doing the work, and it gives you a unique opportunity to do research and then publish that research. Is that something y'all are actively pursuing at Fashion?
I hope. I
Awesome.
wish. I wish because yeah, that's the challenge when we're bootstrapped and we don't have the funds and support to like writing a paper is tough. It takes a lot of time. It takes 1 week to 2 weeks at least if I sit down and try to write what I did. And of course, there's the competitive issue here. Like, what can I do? Like, I worked really hard. Everything is out of my own pocket, and I'm not like a giant. So, for example, Google, they can kind of like flex that they're showing these crazy papers from training on like 64 H100 clusters, and they're like showing their research, and it's kind of like, yeah, like if you have the spare 64 clusters, then you can try to reproduce it yourself. Go ahead. And so they kind of like have the barrier, the moat of barrier to entry that can also allow them to publish this research, knowing that there aren't many labs out there that can even reproduce it. No, they don't have their data, they don't have the talent, and they don't have the hardware. For
Right.
me,
And the money.
I think I did really cool, unique research, and I had some great insights. But once I share it, once I tell people the secret, brilliant people will be able to replicate it if they have the resources. Like, they will be able to understand what I did. They will be able to collect the data the way I did it, and they have much more compute and funds than me. Then they will be able to just do it if they're interested. So, what can I do? So I'm a bit in a pickle here. I would want to contribute as much as possible. I'm for it, but I really don't know how to do it.
Yeah, but also I have to pay bills and live. And so how do you reconcile? It's the classic challenge of open source versus I need food. you know. Awesome. Well, if there's people listening to this who maybe want to support your work or even invest, is that something you're open to? And if yes, how can they reach out?
Yeah, of course. Like we are not against the VC path. Like it's not something that like it's like our principle that we want to be self-funded. But we have other principles which I think many builders would relate to. We want an investor that will understand us. And this is like a problem in fashion and AI. Because our experience with VCs is kind of like this. Either they're really interested in fashion and they can't really appreciate the AI work that is done here. And you maybe after this conversation that we did right now, you probably understand a little bit better, like what am I doing here in fashion? And it's deep work. And not everybody are able to appreciate like real deep research work. And I don't even blame them for thinking that it's not even possible in our modest setup to do this kind of like deep work. So they only care about the use case and how much traction is it gaining in the fashion world. And of course, it's not like we're amazing there. And on the other side, those that do appreciate AI, they're just not really interested in this use case, especially now in these like huge LLMs, agents, and these big enterprise ventures that can happen. Doing like content generation for niche industries and like cool, um, yeah, it's just not that interesting for them. They don't see how can it become a billion-dollar company, and yeah.
Is
So
that is that your ambition to have it become a billion-dollar company, or are you more satisfied with, you know what, we just want it to be sustainable, and of course sustainable with, you know, perks of like we get to live a certain quality of life and so on.
I don't know. I think um, I would love it to happen. I don't see a path to it. I don't want to lie, but I know that what I will continue doing. I will continue solving problems that are needed, but other people probably won't solve because, for example, I can tell you that the next AI tool that we will develop is also something that once it will come out, it will be obvious that it's needed, kind of like virtual try-on. So, and it's also in the domain of image to image, and we keep the text allergy alive. But it's pretty crazy that you have these crazy generation engines, but you still can't take like a logo or a print, drag and drop it into a t-shirt and just have it blend nicely. Nothing can do that. So it's basically an AI mockup tool. So you wouldn't even need virtual try-on. You could just have any kind of pose. You can have any kind of hat. And basically what people do manually in Photoshop, that they use the warping fields and then they use these mockups, and then you will be able to have your own photo, just take the logo and it will blend nicely and you would have this product.
Wow.
And I think it's going to be a great product. And I have a very good idea, very high confidence that it will work. And specifically for this use case, now I do have my own foundational model. I'm not at the same point that we were before.
Yeah.
So I have our virtual try-on model, which is already a very good warper.
Yeah.
So I would only need to modify it slightly. Now I will be in the fine-tuning regime of adjusting it to this new use case of just blending into the logos. So I will continue doing stuff like that. And we will continue building good interfaces for it and help people create content in the fashion industry. And can it go to $1 billion? I don't know. I do think that probably someone would want to acquire us eventually because we have such interesting and unique tech. And at some point after, people will realize it would be better to just buy it than to try to develop it on their own. And this is also kind of like our problem, to be honest. People think that they can do it easily themselves. It's also a curse. Like
Yeah.
every company that we talk about, like you wouldn't believe how many people talk with us saying like, I like your tool, I love it. We will build it eventually in-house, but for the time being, because we need to do proof of concept, we're using you. So we would like to.
That's savage, man.
Yeah, and it's very common actually. It's a lot of people thinking that we are a stepping stone to have kind of like something in place until they are able to do it by themselves in-house. So they have this idea, probably from the ML engineers in-house or from ML advisors. They're thinking, yeah, like with fine-tuning Flux, you can do anything. Just fine-tune it a little bit. It's over. Like it's a new world out there. Like, everything's possible. And so they are fed into that, and it's okay. It's a builder mentality. It's okay. Like I can't say that we weren't similar at when we started out. It's kind of like we're not here because it's easy. It's because we thought it's easy. So I can't blame them, but it's also kind of like why it's hard for us to take the next step.
Well, or I mean, or to take the step of like external funding. It sounds like it's interesting because I had a discussion recently with a very close friend who was talking about this. So you mentioned builder mentality, right? Where it was very similar. It was like, why are we building what we're building? And he said, look, man, I don't know if I'm building $1 billion thing. I just like building, and I like building interesting problems. And he wants to extend his runway as much as possible and just like build something that is truly great in his eyes, to the point where he's like, look, if we get acquired, kind of exactly like you're talking about. And I think that's so precious, actually, because it doesn't concern itself with just money and bottom line and chasing trends and over promising and under delivering that is so common today in the AI space. And so for that, I really do want to applaud the work you're doing. And
Thanks.
I can't wait to see, frankly, I can't wait to see where it goes, especially this like logo placement idea. I can already see, like, at least as an API, like t-shirt print, like Spreadshirt, and all of these merchandise companies already using that and becoming customers. So
I think it's going to be a great tool. Like, it's hard for me to see. Like, this is like really, this was like a very organic idea. This is kind of like the good thing when you're building. Like, this is what everybody says.
yeah,
Like, you start building, and then we're thinking about what is preventing people to onboard to use virtual try-on. And print on demand is a huge industry, and design is a huge industry, and their starting point is mockups. Is They don't even have the clothes. They don't even have a good mockup to start trying from. So there's a huge swath of people out there that can't use our product because our initial step to have some kind of like reference garment from, they're still not there. So for me, it's very natural to help them to bridge the gap from design to on-model photo. I have to give them an intermediate tool so they could bring their design onto some kind of like product without having to use templates for every kind of new product that they're doing. So this came really naturally from talking to people and talking with print-on-demand people. So I know people would use it, and let's see how far it goes. But I think it's going to be nice.
I agree. And that sounds like really great advice. For those who didn't catch what Dan just said, which is an absolute nugget of gold, is when you start building, like, it's not a single path. Like you'll notice forks in the road all over the place, and you're like, oh, I need to build this other thing, and I need to build this. It's literally like a snowball. And kind of like you said, you had this idea for logo infusion into clothes. Just on the process, you discovered a fork and you're planning to take it. And I can speak to that also from my own experience. It's just like I just start building something and build 8 things in the process just because you go down this path. I think
was
that's
even
solid.
surprised it doesn't exist. Like, it comes from, there must be some way to do it. Like, you try, like, and you start to Google search, like the healthiest I think approach is first not to build. It's like, how can I help my users onboard their designs onto my platform, and even buy that and integrate it as an API inside our web app. And you try, and you see there's no way to do it. And so now you're left with the option: are you going to give up on this onboarding process, or you're trying to build it yourself? And if you want to build it yourself, you have some kind of like edge in doing it. And specifically in this case, I think we have a really nice edge to have a cool solution that is leveraging our own solution.
Yeah, totally. And it's a solution that nobody else will have because nobody else has what you have. So it's well positioned. All right, I'd love to wrap it here, but I would be remiss if I didn't ask you for one final thing, which is, there's builders listening to this. You've already given quite a bit of good advice. If you were to like, you've been building fashion with Aya for a long time now. Let's take the biggest lesson you've learned and the biggest thing you want to tell people who are maybe thinking of building something in the AI space or otherwise. What would that be?
It's hard.
That's the point.
I think I would focus on the mental aspect of it.
Interesting.
That even though I think what's unique about the fashion journey that maybe other people can't attest to is that we had a very large incubation period where we had to develop the tech. Like, we weren't sure that it would work. And that was a very scary time because it was months after months after months of failed experiments where the model wouldn't converge, and it took a lot of time to train. And that's a really hard time to overcome, because it would be like I would go to sleep after trying a new run, and I would be afraid to come in the morning and look at the result, because I was afraid of the constant disappointment of, oh, this again didn't work. And when people imagine themselves doing it, they think it would be like, okay, 2-3 months I can handle that. When it becomes 6 months, 7 months, 8 months, when you're doing research, then it's really hard. And I don't even have any tips, to be honest. It's just setting expectations that it could happen, and it's hard. So I'm not sure if it's helpful. But it is a path that could happen that people should be aware, that it's a little bit different from builders that know exactly the value that they're providing and that they can provide value from day one. Like, I really envy those startups, because you know that you can like work on something for a month and start charging people for a month. And we couldn't do that because we really had to develop something as a first step before even trying to sell it. But the reward is that you would have something very competitive, because there really isn't a lot of competition to fashion. Of course there is, of course. But the fact that you have to go through this incubation period basically only puts you up against other research labs. And when you are in an agile startup mentality against cumbersome research lab, you do have an edge. And this is what we're banking on. And so if
You're
anyone...
banking on you're banking on the potential for velocity as opposed to bureaucracy.
Yeah, I think that our agility compensates for our lack of resources in this case. And also, I think our passion for this use case is different from a researcher's passion. And because if I take a look at other big research labs that are doing virtual try-on, I think the researchers there, it's not like they're in love in this task. They are doing research, and they're seeing virtual try-on as a proxy to something related in general to AI. So the idea in itself is very interesting. How do you warp feature? How do you preserve details? How do you don't modify resemblance? Stuff like that. So that's very interesting research questions that it's interesting for researchers to work on, but it's not like they're really into fashion. So they would do the paper, they would do the project, and then they would probably ask to transfer to another project. This is my intuition, that there aren't like research teams that really want to solve virtual try-on out there. Maybe I'm wrong.
Right. So it's a combination of agility, skill, and also passion for the space. I do appreciate your well thought through piece of advice here. And I think if I take a stab at like over summarizing it, it sounds like do hard things. Like set an expectation that there's this incubation period, and it may be difficult and it may happen, but do it. On that note, let's leave it there, Dan. Listen, it's been such an incredible opportunity to learn from you. You have broken down concepts that I've vaguely understood, that I've wanted to understand, that I've taken courses to try and understand, but you've like expressed clear and undoubtable mastery in the subject, just in the way you're able to like translate across domains and across experience levels, and separating latent space from diffusion. And like we are light years ahead of where we started from this discussion in just a couple hours. And so on behalf of myself and all the listeners, thanks so much for coming on and sharing this with me, but also with the community and all the listeners. I really believe you're going to inspire a ton of people and bless their careers. So thank you.
Thank you very much. Thank you for having me.
Thank you for joining my discussion with Dan Bochman. I hope you enjoyed it as much as I did. And believe me, there were moments in the episode where you could hear how much I enjoyed it. If you're considering playing with image generation models, or even making your own, as Dan showed us how we can, then I'm really excited to see what you have. Share it with us. Share it with me on social media. I'm at TejasKumar _. Again, there's links in the show notes. If you're learning from and or enjoying this content, then a great way to support it and really no cost is to just share it on social media. Take a link, paste it somewhere. Let's go. If you're watching on YouTube, then if you like the video and subscribe to the channel, that's a great way to signal to the algorithm that this is useful. As well as if you're listening on Apple or Spotify, just on audio, a review, anything really, up to 5 stars would be super helpful. The goal really is democratizing this information and making it as accessible to as many people as possible so that people can build and have great careers and skills and great lives. And so with that, I want to thank you so much for joining this episode. Thank you for being a part of the podcast, and thank you for your interest in engineering.